Okay, so in the last lecture, we were talking about, we were trying to understand the concept of magnetic forces. And we said that once we understand what the magnetic force actually is, then we will move forward, or we will go forward and try to learn what the torque actually is. So in order to understand what the magnetic force was, we tried to learn what this magnetic force is and how this force becomes maximum, and when this in which scenarios this force becomes minimum or zero. And after that, we moved on and we tried to learn a little bit about Lorentz force, the force which acts on a charge whenever that charge is under the vicinity of any external magnetic as well as electric field, and it is moving. If we reflect and if we try to simulate that scenario, that scenario is the one in which there is a current that is passing through a conductor, so the charges are moving through that conductor, and as a result there is an external electric field plus there is an external magnetic field as well. Whenever in such conditions a current passes through that conductor, there will be two forces acting on that charge. So the sum of those two forces will be equal to the Lorentz force. uh, this was just to make you understand what the Lorentz force essentially is. After that, there we discussed the few differences between Fe and Fm, that is electric force and magnetic force, and then we concluded with the fact that the value of, or the amount of magnetic force, it is it cannot do any kind of a useful work, or it cannot change the kinetic energy of a charged particle, but it can change the direction of motion of a charged particle. That means that it is unable to change the speed of the charged particle with which it is moving through any field, because if that speed of the charge were to uh, be changed by this force, then we will get out from the area of magnetostatics and we will enter into the area of magnetodynamics. So where that is not a part of our course, but still you need to understand that there is no way that the magnetic force can accelerate a charged particle or can decelerate a charged particle or can change the speed of that charged particle. All it can do is that it can change the direction of motion of that charged particle. After that, we tried to understand how the magnetic force acts on a current carrying conductor which is placed under the vicinity of any external magnetic field. And when we understood, when we comprehended the direction of that magnetic force, we moved on and we tried to quantify the relation between the force, the magnetic force that can act on a conductor that is placed under the vicinity of any external magnetic field, with in terms of, with an expression in terms of dl, that is basically the path that the current is following, and the magnetic field. So after that, we saw a little bit. We saw two of the examples in which there was a closed loop, and the other one in which there was an open loop in which the current was flowing, and we wanted to calculate the value of Fm, and then we concluded that the value of Fm for any closed path has to be equals to zero, because the closed integral of dl is essentially zero. Now we will be uh, moving towards another example in order to understand that concept a little bit uh, more efficiently. And in this example, you have been given a semicircular, if I am able to draw a semicircular loop of conductors, and there is a current that is flowing through this conductor. The direction of current is mentioned. This is the direction of current, this is the direction of current, and he's saying that the length of this segment right here is small r, and the length of this segment right here is also small r, and the magnetic field in which this semicircular object is placed, it is B naught, and this B naught is basically in the direction of y. So we'll say that this is y, this is x, and this is z, which is coming out of the screen. So he says that we need to calculate the force on the whole loop. Okay, so we know that in order to calculate the force that is acting on this whole loop due to the presence of this external magnetic field and due to the passage of this current I. So for that case, we need to divide this closed loop into two segments. The first segment is this segment. This is a straight line, and it is very easy for us to calculate the integral by using rectangular coordinate system. And the other segment will be this curved segment. For this segment, we cannot solve this segment by using rectangular coordinate system, so we have to consult the cylindrical coordinate system for this curved path, because we have to take into account the curved nature of this path also. So the b was equals to y hat b naught, and we need to calculate the value of f1. It is given separately, so that is why we have to calculate these two values separately. So this is we need to find the value of f1, which is on the straight path part, and this f2, which is on the curved path of this current. So if we take a look at straight section, the total length of this straight section is 2r. This is r plus this is r, so r plus r is equals to 2r. The current flowing through it is along x-axis. We know this because we have drawn this reference frame, and we know that this is y, so this is x, and we know that the value of current is flowing from left hand side to right hand side. This means that the direction of flow of current is, we know that the direction of dl was always in the direction of the current. Okay, so the l will be x hat, and what is the magnitude? 2r. Okay, so in order to calculate the value of f1, we needed to have I, and we needed to have L cross B. So what we're trying to do here is that we're trying to put the values. So for this case, I is as it is, and then we have the value of L, which is x hat to r, and then we have the value of b naught, which is y hat b naught. So x cross y is equals to z hat, and then 2 I r p naught. So this is the value of f1 for this segment. Now we want to calculate the value of f2, and for f2 we have to take into account this curved segment which is mentioned here. This, if we take an elemental dl, we know that elemental dl for a curved path, that has to be r d phi if we are talking about the magnitude. And if we're talking about the direction, so the direction of this dl, okay, there are two ways to solve this. First of all, if we want to calculate this by using unit vectors, that is going to be a little bit difficult. We will try to apply the concept that we have studied so far, the concept of a right hand rule. So if we're talking about this dl, this will be the direction of dl. We have always told each other that the value, the direction of dl at any instant will be the tangent to that thing. So this is dl, and this is the direction of b naught. And if we want to see what will be the direction of the force that is acting on this conductor, all we have to do is that we have to curl our fingers from dl towards B naught. So if we curl our fingers from DL towards B naught, we'll see that the direction of thumb will be inwards into the screen, and if Z was coming out of the screen, then the unit vector will be minus Z. So in order to make things a little bit easier, we estimated the direction of this force by using a right hand rule. Now what we need to do is that we need to calculate, yeah, we need to compute the magnitude of this thing. So for that case, we have I, we have the integration, and we have dl cross b. Okay, now this is a scalar integral because we have calculated the unit vector earlier. So I is constant. What is dl cross b's magnitude? This is dl is r d phi. So this is going to be r b naught sine phi d. And what will be the value? What will be the value of the limits that we need to put in? It is starting from, we know that the phi is always measured from x-axis, so it is starting from 0 and it is going to pi. So 0 to pi. Once we put these values, the value will come out to be minus z hat 2 I r b naught. So this is the value for f2, this is the value for f1, and if we want to calculate the total force, that is f1 plus f2, so this is z hat 2 I r b naught minus z hat 2 I r b naught. Both of these will cancel each other and the value of the total force will be 0. So this is the same thing that we studied earlier, that whenever the current is flowing through a closed path, and if we want to calculate the force that is acting on the total force that is acting on that whole loop of that current, that is going to be equal to 0. So why did we calculate the value of f1 and f2? Because he has asked us to calculate the value of these segments separately. Even if he didn't ask us to do this, we had to calculate the value of f1 and f2 if we wanted to calculate the sum, that is f1 plus f2. So we had to divide this into two segments, because this is a straight segment, this is a curved segment, this is easy to be solved by cylindrical coordinate system, and this is easy to be solved with rectangular coordinate system. So we had to do this. Baharhal, what we did here was that we practically saw how the value of Fm for a closed loop comes out to be 0. That is, the main concept behind that is because the integral of dl for any closed path, that has to be 0. Okay. So as you know that we talked earlier about torque, and we told ourselves that once we have a proper grip on magnetic forces, then we will be moving towards deep understanding of what a torque actually is. So basically, the force acts on whenever a force acts on a rigid body, so we are talking about magnetic torque of a current carrying coil. Right now we're talking about a simple torque, then we will move towards magnetic torque of a current carrying coil. So right now we'll just write magnetic torque here. Okay, so he says that whenever the force acts on a rigid body and that body is pivoted about a fixed axis, the body will react by rotating around its axis. He is saying that, for example, we have this kind of a thing, and it is pivoted along an axis. What do you mean by pivot? Pivot means that it is fixed along an axis and it is free to rotate around that axis. So we have this thing, and this body can basically rotate on this thing, this stick that is attached to it, and this is actually the axis. So we can say that if this is placed along z axis and this is supposed to be the x axis, then this will be y axis. Okay, so our object here is basically in xy plane, as you can see, and it is free to move around z axis. So it is pivoted along z axis. He's saying that if there is some kind of force that is acting on this object, then this object will react by rotating. Okay. The strength of the reaction depends on the cross product of F, the force. We understood what the force is prior to this topic, and the distance vector d from the rotational axis. The distance vector d from the rotational axis is saying that the strength of the reaction, what was the reaction? The reaction was the rotation of this object around that it pivoted axis. He is saying that the strength, the magnitude of that reaction basically depends on the cross product of the force that is being applied on it and the distance from that rotational axis. So the length, that is basically the distance between this pivoted axis and the point at which the force is being applied, this is called moment arm. This is called moment arm. So the cross product of moment arm with the force that is being applied on that object, this is equals to torque, and its unit is Newton meter. Okay, so he's saying that the unit for torque is same as that of work or energy. We know that the unit for work or energy, it is also Newton meter, but he says that the torque does not represent either work or energy. The force F that is applied on the disc, which is shown in the figure, this is that disc lies in xy plane, as we have discussed earlier, and this force is basically making an angle theta with this d. Okay, so what happens is, if we're talking about the magnitude of this torque, this rotational effect or this reaction, that is df sine theta. Okay, df sine theta, and for this case, what will be the direction of torque? If we are talking about the whole vector torque, that is d cross f. If you curl your fingers from d towards f, from d towards f, from d towards f, then your thumb is going to be pointing towards what? The torque. So in this case, the value of the direction of torque is z hat, and if we change this notation of d to r, this is going to be r f sine theta. This r is same, moment arm. All he's saying is that the value of this reaction also depends on this angle that Fm is making with the moment arm. If this angle is somehow 0, that means that R and F, they are both parallel or anti-parallel to each other. At that time the value of torque will be 0, because अगर आप इसको देखो तो आपका जो D जो है वो अगर इस तरफ को है और इसी तरह से आपका जो एफ है वो भी इसी तरफ को है, और आप ऐसे इसके ऊपर जोर लगाते हो तो कोई रोटेशनल इफेक्ट नहीं होगा, क्योंकि आपका वो फिक्स्ड एक्सिस था और आप उसी एक्सिस के ऊपर जो है वो लगा रहे हो फोर्स, और कोई रोटेशन जो है वो ये फोर्स पैदा नहीं कर सकेगी। तो इसलिए वो कह रहा है कि अगर ये पैरेलल हुए तो एट दैट पॉइंट दी जो वैल्यू ऑफ टी है दैट विल बी 0, और अगर ये परपेंडिकुलर हुए ऐसे और ऐसे, मतलब ऐसे और ऐसे बिल्कुल परपेंडिकुलर, तो उस वक्त जो सारे का सारा फोर्स है वो इसको रोटेशन के अंदर कन्वर्ट करेगा, एंड एट दैट पॉइंट द वैल्यू ऑफ टॉर्क दैट इज गोइंग टू बी maximum. So the right hand rule, torque in z direction, shows that the tendency to rotate in a counterclockwise direction, similarly minus z clockwise. तो if we are talking about z, तो z का मतलब ये है कि हमारी जो ये था हमारा d, ठीक है, और ये था हमारा एफ, और हमने फिंगर कर्ल की एफ से अपना डी से या आर से एफ की तरफ, तो हमें डायरेक्शन मिली जी। ठीक है, तो जी का मतलब ये है कि मेरा जो ऑब्जेक्ट है वो काउंटर क्लॉकवाइज जो है वो मूव कर रहा है। अगर जो है वो मेरी फोर्स इस साइड पे लग रही होती ऐसे करके, सॉरी ऐसे करके, तो उसके केस में हमारे पास जो वैल्यू निकलती टॉर्क की वो माइनस जी निकलती, यानी कि इस तरफ को निकलती, और उसका मतलब ये होता कि मेरा जो ऑब्जेक्ट है वो क्लॉकवाइज मूव कर रहा है। ठीक है, तो ज़्यादातर जो जब भी आप टॉर्क को कहीं मेंशन किया हुआ देखोगे, तो जो इसकी एक्चुअल डायरेक्शन है इन द फॉर्म ऑफ यूनिट वेक्टर, दैट इज रेयरली मेंशनड। All that we mention is the magnitude of torque, and we mention that either that torque is clockwise or counterclockwise. So he's saying that if in this case the direction of torque comes out to be z, then we know that by right hand rule the direction of rotation is going to be counterclockwise. But if the direction of torque comes out to be minus z, then by right hand rule we will see that the direction of motion is going to be clockwise. So what I am telling you is that you will see that mostly how you mention torque is that you mention the magnitude of torque along with the direction, but you do not mention the direction in the form of unit vector. uh, Instead you basically say that this is the magnitude of the torque and it is in clockwise direction, or this is the magnitude of the torque and it is in anti-clockwise direction. As this is a rotational concept, so there are only two things: either it can be clockwise or it can be counterclockwise. So by right hand rule, the clock we now consider the magnetic torque averted on a conducting loop under the influence of magnetic forces. So for that purpose, what he is doing is that he is taking a simple loop. We'll take another whiteboard for that. He's taking a simple loop. In that simple loop, this is like that simple loop. He's trying to understand uh, the concept of torque for a simple loop which is carrying current. So if this is a simple loop and the width of that loop is a, okay, and we'll say that this loop is placed on xy plane. So this is going to be x-axis, this is going to be y-axis, and he's saying he's labeling this as this is the first segment, this is the second segment, this is the third segment, and this is going to be the fourth segment, and the direction of current is going to be this way, counterclockwise, and the length of this is going to be p. Okay, and he's saying that we have an electric field, sorry, which is uniform and it is along x-axis. Okay, so this is the most simplest scenario for us to understand what the concept of torque actually is. And the one more thing that he's saying, that this loop is pivoted along y-axis. Okay, so it can rotate along this axis, this y-axis. So what he's saying is that this loop carries current I. Okay, the loop is in xy plane, जैसे हमने पहले explain कर लिया, the loop is in xy plane. Okay, and the value of b is basically uniform and it is in the direction of x, as we can see here. So if we want to calculate the value of f1, f2, f3, f4, because we need to have the value of these forces if we want to calculate the value of torque, because we know that the value of torque is F cross D. So we need to know what is the value, D cross F, sorry. So we need to know what is the value of R cross F, sorry, R cross F. What is the value of this F? Okay, so we have to calculate the value of forces for all these segments. So let's move toward the calculation of force on the first segment. The first segment is, you know, F is equals to I into L cross B. So all we need to do is put the actual values here. Uh, what is the first segment? This is the first segment. So this is the actual length, and which is basically B, and it is in the direction of minus Y. So minus Y hat and B, and then cross product with B naught, which is actually X hat B naught. So Y cross X, this is going to be equals to a Z hat I B and B naught. This is F1. What about F2? F2, this is the second axis. This will be the direction of current. So for 2, the force will be 0. Why? Because L and B, they are anti-parallel. So even if they are parallel or they are anti-parallel, this product is going to be 0. So F2 is 0. If we talk about F3, for F3, once again, we will put the values Y hat B cross X hat B naught. This is 3. Now the direction of DL is in the direction of Y hat. So once again, minus Z hat I, B and B naught. So this is F3. If we talk about F4, this is also going to be 0 because L and B are parallel for that case. So we have F1 and we have F3, and we do not have any kind of force that is acting on the segments 2 or segment 4. So what he's saying is that now we do have the value of forces that is acting on this thing. Now we need to understand how it will rotate, how the concept of torque is going to work in this case. So he says that what we'll do is we'll try to take a look at this loop from bottom. Okay, so from, if we take a look at this from bottom, we will mention it something like this. Okay, if you take a look at this from bottom, you will see this coming towards you. That means you can show this by dot. And if you see this, you will see the current going away. So you can depict this by cross. So this is the pivot point, this one. This is the pivot point. And this whole thing was equals to A. So we'll have A by 2 here and A by 2 here. And if we're looking at this loop from the bottom, then we know that the Z is upwards. So the F1 that was being applied on uh, the first segment, that will be in the direction of Z. So this was F1. And when we take a look at this, this was into the screen minus Z. So this is here F2. So this is minus Z hat. Okay. Now we see that this is F1. So this is the moment arm D1. This is F3. Sorry. So this is the moment arm D3. If we want to calculate the total torque will be torque due to 1 plus torque due to 3. 2 and 4 were 0. So D1 cross F1 plus D3 cross F3. So what is the value of D1? Once again, take a look from here. We said that the D is basically from pivot point to the point from which at which the force is being applied. So this is basically the value, or this is basically the direction of D, and this is minus X. So minus X hat, and what is the magnitude? A over 2 cross F1. F1 was C hat I B P naught plus D3 was x hat a by 2 cross minus z hat I p and b naught. So when we add it up, this is going to be y hat I small a small b p naught. And we know that small a and small b are length multiplied by breadth, that is equals to a. So we'll say that it is y hat I a p naught. So this is the total torque that is acting on this thing, this for this case, for this scenario specifically. But this is valid only when b is parallel to the plane of loop. This is only valid when b is actually parallel to the plane of loop. As soon as this thing starts moving, it goes into this direction. Now the b now the b is not parallel, because this was b. Now the b is not parallel. Now the b will make some kind of an angle, and for that case the value of torque will start to reduce. Okay, so we'll see that concept in the next lecture, but I will urge you to try and understand that concept yourselves. I will be talking about it in the introduction of the next lecture, and I will ask from you people if you understand that what will be the relation or what will be the effect of that angle that the bee will now make with this loop whenever it starts moving, and why does the value of torque will start to reduce once this loop starts rotating on its axis. So we'll be talking about this. I think that is going to be a healthy discussion. And if you so far this is it for today. If you think there is some kind of ambiguity, some kind of confusion in anything that we have studied in this lecture, you are welcome to ask that in the interactive session. Next time we will move towards the scenario after which this loop has started moving. So for now, this was the magnetic field in the plane of loop. The next time the topic will be the magnetic field perpendicular to the axis of rectangular loop. So we'll be moving towards that. This is it for today. Thank you so much.